the sides at the midpoint, and the easy thing that you know, it's going to have to obviously bisect it both ways. Whoops, I missed. And that's immediately going to give you a 30, 60, 90 right here. And you know that where you end up there has got to be at the center. So, yeah, because that's going to be true as you rotate it in each 120 degrees each time. Since it leads you to the same point, it's got to be the center.
How do we get a value for that we can use?
Oh, in terms of finding coordinates, I mean, I suppose you could maybe call the origin right here. And so then, do you mean how do you get, I mean, obviously things that you want to know are things like that and this position and a bunch of trig, right? I think I would have, I mean, the typical thing to do would be to give you A. So I obviously know this is half of A. And then you know, since this is a 30, 60, 90, that little guy, that these side lengths are 1, 2 to root 3 ratio. So you can just start playing games like that. You know, set up like A over 2 is to root 3 as the thing that we want to know. Let's call this, I call it Y. Maybe Y1 as Y1 is to 2. So you could literally like Y1 over 2 equals A over 2 over root 3. And, you know, just play around with 30, 60, 90s for 20 minutes and you'll have everything you need. Yeah, I think probably the y coordinate of these guys is the ugliest of the expressions, but it's still solvable, obviously. And just a bunch of different 30, 60, 90s within that triangle that you need, right? Any other thoughts or questions? Oh, I guess I left you with that problem to work it out. And did you do it vector-wise, or did you do it, you know, using symmetry and magnitudes? Because I think in that case, symmetry and magnitudes was the easier thing to do. Did anybody finish it? Did you finish it? Yeah, yes, but you're not sure you're right? Okay, well, we can start with that. Where are we on time? I guess class starts in a minute. Why don't we, I guess we can pray and then we'll get started in class. We'll start with finishing that problem, and then the real goal for today is going to be continuous charge distributions. If you, this here is our Teams group, so if you aren't yet in Teams, I'd recommend it because, among other things, you can rewatch lectures, you know, because they're all posted there. And through the Teams group, there's a class notebook, which means you can get to anything that I've written in OneNote. And for instance, I don't want to turn on the screen right now, but I guess I could because it doesn't interfere with the whiteboard. But what I also turns the lights off. What I'm putting in OneNote is photographs of the work that we've done in class. So, for instance, last time's, come on. So, you know, screenshots of the board that you'll be able to zoom into and see the work that we did. So, anyway, use this code. And yeah, we'll come back to this in just a minute. Why don't we pray, thank the Lord for, well, it's an important Monday, isn't it? Lord, we come to you and thank you for a brisk morning and Martin Luther King Day and also presidential inauguration today. And just in the context of the latter, I pray that you keep the proceedings safe, you know, that nothing crazy happens. We seem to live in a world right now where people like to incite difficulties, riots, whatever. Have your hand on the proceedings, and just pray for your perfect will to be accomplished, however that, whatever your plan is, to make it come to pass. Thank you for this time, and open our minds even to things as simple as laws that you've implemented to run electromagnetic phenomena in our world, and help us see that as part of of your glory, and dedicate this time to you in Christ's name. Amen. So, yeah, let's finish that problem first. So we left off with the equilateral triangle. Do you want to tell me what you did? So same picture as over there, except if we go with the symmetry route, we first of all discussed the fact that, did I label these 1, 2, 3, and the 4 in the middle? I think that's what I did, right? Yeah. All right, so.
2 is on the bottom left.
Did I go counterclockwise? All right, good. So, oh, what did I just do? That's weird. That was an interesting brain move. Okay, so I think we talked first about the fact that if one of the corners is satisfied, then all the corners are satisfied. Are you, and that is so long as these 3 charges are the same magnitudes as one another and sign. Is that clear that that has to be the case? Like that if one of them has no force than the other? Okay, so, and you know, if you're still thinking like, but how do I know for sure? I mean, imagine this, I'm doing this problem, I'm like, hey, what's that? And I turn this thing 120 degrees and you look back and I'm standing here like I did nothing. You couldn't tell the difference, you know, having rotated this triangle 120 degrees because it has the same charge on each corner. So obviously, like, what are you talking about? 3 would be up here. I'm not talking about the labels, I'm talking about the physical thing. If the charges are the same, you rotate it 120 degrees, you couldn't tell. And if you can't tell, then the point is it's not a different problem to be solved. And so if one corner experiences no force, then the other 2 as well have to be in the same situation. We also talked about the fact that this guy, if it's sitting symmetrically in the center of this triangle, also experiences no force. And that one, I think what I suggested is that you can work it out to be sure, but the situations that are easy to convince yourself of are when you have even numbers of charges around the central one, like 1 on each side like we did in the case of 3, or put 1 charge in the middle of a square. It's easy to convince yourself because they're always paired up forces from opposite sides that cancel. Even though there aren't paired up forces in the cases of odd numbers, it still works out just the same, that the one in the middle is balanced. And if you're not convinced, either I can make a homework problem so you can convince yourselves, or you can just go do it to satisfy your curiosity, but it's true. So essentially this boils down to, if I can focus on one of these, I'm going to take this guy and find that it has no force on it, then everything is in equilibrium. Quick question just to recap, is that a stable equilibrium or an unstable one? It's definitely unstable. And all right, so the goal, if I maybe use different colors for the different forces. So how about we do this? I'll make this guy green, and force on this guy due to that guy. Which way does it go? Yeah, away from 2, right? And we know that it's away from, why do we know it's away from and not toward? Yeah, it's the same charge, and that means same, not just magnitude, but also sign. And same signs obviously repel. So the blue number 3 pushes diagonally up in the right. Green 2 does the opposite, but to the left. And then what is 4 going to have to do? Straight down. And the only way it can be straight down is for the signs, obviously, to be opposite one another, meaning whatever the 3 corners are, because they have the same sign. Let's say they're positive, this guy has to be negative, and vice versa. All right, so now we just need to figure out how we can take those 3 vectors and make them add up to 0. And how do we go about doing that? I'm going to bisect this angle. What is the angle here and here? Not everybody at once. I can't hear when it comes in like that. 30. Yeah, 30, because it's a equilateral triangle. It can't be anything else. So 30 degrees there, 30 degrees there. Why do I care? Yeah, so the rightward portion of the blue one cancels the leftward portion of the green one. So if you imagine this, why don't I extract them from that maybe I'll make them solid lines just so we can see them more easily. And the green one going this way. What we have going on is, well, whatever the leftward component of that is, whatever the rightward component of this one is, they cancel, right? Cancel because how couldn't they if they're symmetric around the vertical axis? So we don't have to worry about left and right components, so what do I have to worry about? Just the vertical, and they add up. So you could draw those where you wanted. I'm going to draw them right here just to make it look like tip-to-tail addition. I got that upward component, I got this upward component. Of course, you could also draw them here. You don't have both forces, but it's a matter of how do you want to visualize the breakdown of the vectors. Either picture is fine. But you have those two upward components, and how big are those upward components? So those, the upward dotted ones, how would you find them? Just in terms of, if I knew that this total vector had, let's say, magnitude f, and the direction where it's pointing, how big is the upward component? Upward components are f times what? Which trig function? If we're using that 30-degree angle. Yeah, which one? Cosine or sine? Cosine. So when that angle goes to 0, the cosine of 0 is what? And that would be what we'd expect. If this angle went to 0, then all of it is upward, and you'd get it right. So they are each cosine up with the 30 degrees in there, because we already know that. So then my issue is really, so this is, I'll just call it f. I'll just call it upward. So the f upward component is whatever the magnitude of the forces would be, each of them, times cosine of 30. And so really maybe what I should think about this is there's two of them, because there's the blue one and there's the green one. This is the, whatever that f value is for each of them, it's just its magnitude times the cosine of 30 degrees. How do I find the magnitude of the force between the 1 and 2 or 1 and 3, which is what we're after? Coulomb's law. So this guy comes from, well, what's the equation that I'd use? And again, remember that I had labeled it like we know A, the side lengths, and they're all the same. Yep, K times Q1, Q2, but they're both the same Q, so maybe I should just write it as Q squared, and then yep, yeah, that's the easy way in this case, because all I care about is the magnitude. And so, just rewrite Q squared over A squared. And Q is, the assumption is we're writing that's Q, this is Q, and this is also Q, and we'll give this guy a different label, capital Q. All right, so we have the up. Total up is 2 times this thing, K Q squared over A squared times cos 30, which of course we can replace with root 3 over 2 if we want to, but so what else do we need to do? What other force is acting on the one on the top? Yeah, there's a downward one, so that purple vector that we have there, and it's only downward, so we don't have to worry about components, of course. So how do I get that value, the f, downward? Yeah, K, the little q is Q1 at the top. This guy is representing the one in the middle. And then over whatever that distance is, and what did I call it over there? I called it y. So this distance here, we'll call it y1, as in how far 1 is from the center. And before class, we'd had this discussion. You can break down this triangle into, the overall triangle like this, so that if you look at that, obviously this is a 30, 60, 90 right triangle. And if the whole side length is A, then half of it, which is what we'd have to the, pointing right at the center, is A over 2. And if you set up the ratios of A over 2 is to y1 as root 3 is to 2, then you get this. And what does that mean? Y1 is 2 over 2 root 3, or it's, oops, A. And so it's just A over root 3. Does that, I think, sorry, Y1 is what I was calling it. Yeah. So this is denominator A over root 3 squared. That's, and of course we understand that because it's downward, and this is kind of the downside of using magnitudes and kind of intervening in the calculation instead of using Coulomb's law as a vector expression, is that I look at this and I know that it's downward only because these guys take on opposite signs, and so you just can't forget that. But magnitude-wise, everything works out. And then what's the last step if I have the up and I have the down? Yeah, we need the up to equal the down so that in total there's no net force. So we need F up plus F down to equal 0, or equal and opposite. So let's write 2k q squared over a squared cos 30 degrees plus, or if we, why don't we do this? We'll equate magnitudes. How about I do it like this? Equate magnitudes, and then we'll put the the flipping of sign manually, equals k, q, q. Maybe we should, well, let's break this open. So this is a squared over 3, which means the 3 goes up here, right? All right, so then we can cancel a bunch of stuff. And maybe we should substitute for the value of cosine of 30. But first of all, a's don't matter. One of my q's doesn't matter. And this is, if I replace this guy with a root 3 over 2, then where do we find ourselves? We have, so what's left now is, I guess the 2's cancel, so I get q times root 3 is what I have on the left, and 3 over q on the right. That's what it looks like. So why don't I just write it as, how about we write it as root 3 times big Q equals little q. And that looks like the whole story. And what's the last thing that I have to manually insert to make this expression true? Yeah, I need to stick a sign somewhere, so let's put it there, one side or the other, so that we know that they have to be opposite in order for them to have been attractive. So, do you make sure I didn't make any mistakes on the algebra? Cosine, it's definitely root 3 over 2. 2's cancel. K's, 1q, both a's. Root 3 over root 3 is root 3. Q. I think it looks good. So, any questions on that? There are multiple things that this tells us. First of all, it doesn't matter how big the triangle is. Does the size matter? No, it's gone from the expression. Right here we found out it makes no difference. And of course the ratio of the charges matters, but certainly not the absolute magnitude of them. And fundamental constants like k doesn't matter, so in principle, if there was a way to play this with gravity, and there isn't because we don't have this idea of repulsive gravity, but if you had a different fundamental force of a different strength, which is really relayed to you by this k value, it would still work. But anyway, any questions about any? Yes?
Could you explain the sign change there?
Yeah, if it wasn't true that the one in the center and the ones on the outside were opposite signs, then instead of pulling the top one downward here, it would be just helping spread them. It would be pushing it out, and then there's no way that it could balance. So.
Okay, and just at the end of the equation, you flip the sign.
Yeah, and the reason that this is sort of something that we need to throw in is because really when we started with calculating magnitudes, what the burden was, okay, I know how big the force is, but I'm kind of manually assuming that one of them is going to be downward and the other ones are going to be outward. And so we weren't leaving it to the math to figure out the directions of the vectors.
Okay.
We were just saying, oh, I need it to be attractive, so downward.
Yeah.
And so
So that's just tacking it on at the end because we know how it works.
Yeah, that it wouldn't work if this wasn't the case, if it wasn't opposite signs, because things would just spread. All right. So switch gears to a slightly different problem? Yeah.
Could we at the beginning of the problem have set the force upward added to the force downward equal to 0, and then we wouldn't have had to do this?
Yeah, but you have to, so his question was, could we have said the up and the down equals 0? If you, the short answer is it looks like it would work, but I would be very reluctant to assume that it's going to work every time. Because of this awkward, suppose we started with a homework problem where they gave you signs, and one of the things was from the outset assumed negative. And then you started calculating magnitudes of forces. And then you'd put in these manual directions knowing that they need to cancel. You can find yourself like canceling a negative in a way that you don't want to if you do problems like that. And so I think it's much safer to not assume that it's like sum of the force. So many times when we did, I don't know, let's say sum of the forces equals MA back in first semester, we would say, oh, this really means that by components of sum of the forces in the x equals MAX, and sum of the forces in the y equals MAY. And there were lots of cases where we found the x component of forces and added them up and set them equal to 0, or found what they equaled. But it's different to add up components of vectors than it is to take two terms and say the up equal, plus the magnitude of up plus magnitude of down equals 0, because the difference is that these guys retain their signs. The x components of vectors can have positive or negative signs, and so you're adding them not as magnitude plus magnitude equals 0, but as, well, the sign is telling me which way it's going. And so it's a different thing. And so I really think the better way to do this is find the magnitudes and think of up plus down just to relate magnitudes to get things right, and then pause at the end like we did and make, oh wait, I know the signs have to be opposite. And that way you just don't get in trouble. Or if you just don't want to think at all about it, then use the bigger equation where you put in the coordinates and use the version of Coulomb's law that actually is a vectorial version. It's a little bit painful because you have to work out the components of everything, but there's no way you could get the answer wrong outside of just a careless arithmetic issue or something. All right, so probably shouldn't have erased that because I wanted to take pictures of the screens. Let me do that real quick. Oops, kill that. Wake up. Why are you going to sleep? You're like a student. What is this? Wake up. Lecture. Why are you doing this to me? Oh, password. So next thing that we're going to discuss, as long as my computer doesn't prevent it, is the idea of extended distributions of charge. And one thing that you'll notice that's, we talked about similarities to, do I not have a camera option? I gotta have a camera option. Insert. Well, maybe from pictures it'll let me use them. From camera, good. Wake up. There it is. Photo document whiteboard. All right. That was blurry. Let me do that again. Yeah. So with gravity, something happens automatically. I'll fix this later. Remember when we had the universal law of gravitation? We wrote force of gravity equals g m1 m2 over r squared. And we were always, so the idea is one of these might be Earth and one might be the moon. And distance of separation is r. And we could always just be sure that the force was attractive, and I didn't really ever need to ask, well, wait a minute. Mass of the Earth, mass of the moon, distance between them. Is that the distance from the front edge of Earth to the front edge of moon, or is it the middle of Earth to the middle of moon, or is it does it matter? What if Earth had the same mass, but it was a less dense object, so it had a bigger radius? And so it's worth asking, does that matter? first of all, which R is the correct R to use? Yeah. Yeah, it is center to center. And then the second question is, does it matter then how big the thing is? Do I need to, if Earth was so big that it nearly encroached on the orbit of the moon, like here it is, but its mass was still exactly what it is, would the moon have a different orbital trajectory? And so it's an interesting question and not an easy one to answer. And the answer is, well, it actually doesn't matter, but it doesn't matter because of one convenient fact, and that is the spherical symmetry of the planet. Now, the planet isn't exactly spherical, so in actual practice, it matters a little bit. Some tidal influences would be different in the big case versus the small case, but let's skip all that and assume that Earth is a perfect sphere. In perfectly spherical situations, we never need to worry about the distribution of mass in order to figure out how strongly two things are attracted to one another. Meaning that whether Earth was gigantic size but not mass, keep its mass constant, but whether it was this big, or whether it was squeezed down into something the size of my fingernail, it doesn't have a different gravitational pull on objects at a distance, so long as that distance is obviously held fixed. So the convenient part is that it's spherical, because this isn't true for anything but spherical objects. And so gravity has this tendency, though. Well, first of all, it's a really weak force. And it's weak in the sense that if you compare it to, well, the other major force that plays into our lives, which is this electrostatic one that we're talking about this semester. In my lecture last year, last term in 231, we often started with fundamental forces and had discussions about how weak is gravity comparing to the electrostatic force. And you have to have a situation where it makes sense to compare them. But consider chemistry. Did you take chemistry? You did, right? No? Put your hand up if you didn't. Why not? Is it on your, a future course still that you're in?
Computer engineers on
What? I'll cry about that later. I mean, it's not like it's physics, but it's a consequence of physics, so it's nice to know about. Did you take it in high school, though? Okay, so if you, did you guys in high school discuss the Bohr model and things like that? So that it's a very bad model, actually. It's far from correct. And it's a good discussion. Why do we still teach it when we know it's completely wrong? Maybe the completely is the reason. It's not completely wrong because while it's a terrible model, it makes a few good calculations possible. Not good as in how you did them, but good as in the number happens to match up with what we can measure. But the model, of course, from Bohr is that there's hydrogen only has a proton in the nucleus if you take the most abundant isotope, meaning there are no neutrons. And then there's this tiny electron. So there's the proton and playing the central body, if you think about this like gravitation, and an electron. And the idea, which is the part that's really, really bad, is that you imagine that this electron is orbiting the proton just as Earth orbits the sun. And so if we made a comparison using a naive model like this and said, well, okay, so what's holding it together? Gravity obviously keeps the Earth in orbit around the sun, so what's helping this electron orbit around the nucleus? And what's the answer to that? What force? Yeah, so there's this electrostatic force. There's the fact that this one's positively charged and this one's negatively charged, and they're attracted to each other. But isn't there a mass of a proton and a mass of electron as well? There are. And so you would have to think like, well, wait, the force, the centripetal force, if you think of last semester, that would keep the electron orbiting, there's two of them. There's the electrostatic one, which we should think of as the Coulomb force, this thing that we've been calculating all along. But there's also a gravitational force, force sub g, which is given by this guy. And they're both attractive. If you go into any chemistry textbook, they don't mention this, that there's a gravitational force holding molecules and atoms together. Well, that's an oversight because there is gravity. It turns out that it's not relevant. And the only reason it's not relevant is that the magnitudes are nowhere near like I drew those vectors. And if you run the math, well, how would you run the math if you wanted a number for this? How would you figure out how much stronger? So here's the force of gravity, and how about I do this? One of these is a proton, one of these is an electron. You have to know how far apart they are, or do you? We'll look at it, but this is the Bohr radius, often called A sub 0. 52.9 picometers, it's tiny. This is that gravitational constant. We can plug that in a minute, but the Coulomb force in comparison, well, we have that K value that I got wrong on the first lecture, but we'll try to get it right this time. And then the charge. Well, it turns out the charge, Q for an electron, they actually call it E, and that is not because of the word electron necessarily, but it's an electrical charge that is the fundamental charge. It's the exact same magnitude on the proton as it is on the electron, except that they're opposite in sign. So this is really by magnitude. It's E of the electron times the same E for the proton, which makes that E squared. And then the distance, the same thing that I'd plug in, the same value for A sub 0 in both equations. So an easy way to compare them is ratio, right? And that's what I would have done in 231, just to point it out. So how about we do this? You calculate the ratio of the Coulomb force to the gravitational force. And that literally just means I can write this as this guy over that guy. So K E squared over R squared divided by G mass proton, mass electron over R squared. And of course, I don't even need to know how big the thing is. So it's a bunch of constants, fundamental constants. And if we look at these numbers, 8.99 times 10 to the 9 is the correct value for K. I don't know how I did that. Newton meter squared per Coulomb squared times fundamental charge, which is 1.602 times 10 to the minus 19 coulombs. Square it, and then divided by G, 10 to the minus 11 Newton meter squared per kilogram squared. Mass of proton, 6.7. No, that's the charge. Or is that right? Can you guys check the mass of the proton? I think it's 1.67 10 to the minus 27, but check if that's right. Check if that's the mass of the proton, and then mass of electron.
Yeah, 1.67 times 10 to the negative 27.
Is the electron right also? 9.11-ish?
Yeah.
After that first lecture, I just have to, I'm sitting here like, I don't know. Okay, so look at these numbers. Even if, whether you want to plug them in exactly or not, what we have is, oh my, 10 to the minus 38. So 10 to the minus, call it 28 because that's almost 10. So 10 to the minus 28, 10 to the minus, 18, 17. Oh wow. These are going to make huge positive exponents. And if you do the math, you're going to get like 10 to the 39th power, I think. Is anybody running this? This is approximately 10 to the 30-something. I think it's 9. I'll leave that to one of you to figure out for right now, because you have calculators and I don't have one on me. But the number is gigantic. What does that mean? What does it mean if I get a number like 10 to the 39? Yeah. Oh, that's not a hand up, but you're committed now because you're fixing your hair. I'm like, oh, answer.
It's because the body's like so small.
Yeah, or in comparison, which one is absolutely gigantic to the point of don't need to worry about the other? Yeah, so the Coulomb attraction is so much bigger. Think about that number. There's nothing, no wealth of Elon Musk, in dollars that even comes close to that, right? You're like, okay. Guys, the national debt, 20 orders of magnitude less than that at least. So in any case, the point is, why do I need to not care in chemistry? Because this guy's so tiny that if I drew these to scale, you don't even see it on the picture. And it doesn't affect anything. And you're like, well, anything? Like, yeah, because unless you're going to have precision of measurement of energy levels of electron orbits out to like 35 decimal places, you'll never notice it. So it really has, I don't want to call it zero consequence, but essentially 0, yeah.
Do we see any, like, proportional electrostatic forces, like, in similar sizes to, like, gravitational forces between the Earth and the Moon?
Oh, you mean, can we charge things such that, well, the one thing that you tend to find that's rather different than gravity is that the overall, as far as we know, the overall charge of everything in space, even locally, not just universally, tends to be 0. So you can end up having dipoles, but you can't find situations where you have a gigantically charged object and another one that, you know, it really, I mean, because the force is so big, you can't even end up having like Moon super positive and Earth super negative. It's just never going to be that way, because there would be, we'll talk next chapter about the fact that generates a huge electric field, which then is going to fix the situation by rearranging charges, you know, flinging them through the vacuum of space and trying to neutralize everything. So not really. But you can easily, for small objects, you know, find electrostatic forces easily outdoing gravity. I mean, for one thing, it's happening right now. I'm not falling through the floor. You know, it's a weird idea, but you know, if you think about the entire planet, if its intentions were met, it would suck me into the center of the Earth, because gravity's trying to pull me in and down, and when the only time that would stop is when I'm symmetrically sitting in the center of the planet, and yet all it takes is a few, you know, molecules on the bottoms of my shoe and a few on the surface of the floor to be like, no, can't do it, gravity, sorry. You know, the electrostatic repulsion that's saying, no, those electrons can't occupy the same space at the same time, and in spite of an entire planet's tug via gravity, that little tiny surface of my shoe is enough to be like, really? You're going to keep trying? All right. And so the convenience side for gravity is this. Because it's such a small force, it doesn't tend to matter until you have really big objects made of mass. You know, like, you don't have to worry even when you, there's a Kings Canyon in California is a fantastic place to go visit. Beautiful sequoia trees in the forest nearby, but there's a rock face that's ridiculously tall, where one side is kind of forest and the other side is like, oh my gosh, it's a giant rock face. And if gravity was, even with, I mean, when you think about, I have these rocks in my yard that they made a fire pit, the previous owners of the house, and I really don't think it's in a good spot. And because when you make a big fire, it tries to kill these plants that my wife likes because the heat gets on them. So I had the idea of trying to move them. Rocks are heavy. You know, just a modest-sized boulder, it's like not a chance you're going to move it. So you get out a tractor, and I had to buy a little tractor, but it has like a 1,100-pound bucket lifting, and it's like just making this grinding noise because it can't do a darn thing against this rock. I'm like, wow, okay, I give up. I'm not going to hire a guy with a bigger tractor. But you know, when you think about the density of rock, you go to Kings Canyon and there's a rock wall that's about, you know, thousands of feet high, and you're thinking like, okay, that's a lot of mass. And so maybe when I stand here, it's going to be like, like, stop pulling me, you know, and you get stuck to this wall and you're like, somebody help? But of course it doesn't happen. You don't even notice having to lean a little bit away because gravity is so pathetically weak. You know, it literally takes not that rock face, but, you know, to the scale of things, that rock face is nothing if you're looking at Earth from space. And the entire Earth pulling us downward feels about like this. And that's still not me being stuck, because I can easily jump and disconnect myself, right? So gravity starts to matter when you have enormously big things. And enormously big tends to be things like the size of planets and moons and stuff like that. We don't have to worry about huge gravitational influences when comets pass through the sky, because it just doesn't matter, and it would be so small that we wouldn't measure it. And what's convenient when you have gigantically big masses is that materials tend to get crushed by their own force into spherical shapes. So in the event of the rocks in my garden, they aren't spherical, but it doesn't matter because gravitationally I'm not going to be attracted to them in a way that I care about. But when you get things that are big enough that their gravity matters to us, generally they tend to be so big that they're like the size of the moon, that gravity between the moon and its own pieces has crushed itself spherically symmetric, and you end up in this nice situation where you never need to worry about, well, how is it distributed in space? Because the how does matter if it isn't spherical. So for gravity, the problem fixes itself almost always, you know, and that is that things tend to be crushed spherically, and then I only have to worry about here's one spherical thing, here's another spherical thing, how far are their centers apart, and I can work out the math like this. Electrostatics doesn't work that way, because, I mean, I could take this guy and here, rubbed it on my coat, and guarantee you there's a charge buildup, and it's a linear object, and it's stuck there in this linear configuration. And I might say, well, what if I put a little piece of lint right here? What happens when I let it go? There's going to be a force because there's charge, and even if this lint isn't charged, we'll talk about how it'll have an induced dipole moment. And so there's going to be an attraction between them, but it isn't spherical to spherical. It's a distribution of charge that in this case looks like a line. And so you find that everywhere in nature. You know, same story. It's like, all right, now I have a plane-shaped surface that is planar geometrically that is going to have an influence to everything in its surrounding. And that planar surface doesn't, like gravity, crush itself into a sphere. And so the math gets much tougher. And that's a good portion of what we do, really, in this course, is deal with, well, what if things aren't always simple and spherical, and I can't just plug it into an equation that you could have done in 8th grade, but instead have to find an influence for some distributed system of charges. So I thought a nice way to go about that is to not forget to take a picture. And anybody want to expedite picture taking by makeup? Nice way to go about it might be to look at it in a series. Actually, I'll take that picture later so I don't lose time, and I'll just do it over here because I already have this picture. So take that linear situation, because linear in 1D is the easiest place to start. And suppose that I'm interested in answering a question like this. Here is some object like the marker, and it has a length that I'll call L, has a total charge on it that I'll call Q, and then some other charge. For now, we'll assume it's a charge, but it turns out that this one, like I said, will in fact be attracted whether it's charged or not. But for right now, we'll assume this thing is small, so we can think of it like a point-like object, and we have to define how far it is from at least the edge of this object. So what's going to happen? And of course, if we didn't know how to do series or eventually calculus, what do you suppose the best thing I could do to approximate this would be? How would you try to approximate the force between those two things?
Without any calculus, I guess, assume a point charge from the center.
Yeah, so I think most people would realize, like, I shouldn't take all of this charge and assume it's sitting as close as possible, nor as far as possible. And if you had to choose a point, you're like, hey, you know what, right in the middle. So you'd say everything is sitting right there, meaning all of this charge, we'll just assume it sits at one point, right at the midpoint. And so we'll call this F1. 1 because it's one piece at the moment. I haven't chopped it into pieces, and you'll see how that plays in a minute. But if I did that, the force would be, at least magnitude-wise, K times Q of that guy times Q of this guy over distance. What would the distance be?
A plus 1/2 L.
And then I have to square that because it's Coulomb's law. And that's my roughest possible approximation to the force between them. But how could I do better? If I called it like F2, and let me see, maybe I'll draw it here. Same picture, except I'm literally going to do you one better, and that is, instead of thinking about all of the charge sitting at the center, what's the next best thing we could say? Like if I chop the charge in half, where would I put those two pieces? Yeah, so how about I do this? At the middle of this half, I'm going to stick Q over 2. Middle of this half, I'm going to stick Q over 2. This is still A. The total is still L. So we need an expression for this. So F2 that goes along with that picture. What's that going to look like? Obviously, this part doesn't change. But we need a distance between, well, there's two terms, aren't there? So first term, meaning force between this and that. We need the distance. So first of all, the charge is going to be Q over 2. You with me there? So point charge, the way we're going to think about this is this guy's, the force between that object and this charge is the sum of the force between these two pieces and these two pieces. So this is going to have two terms. What's the distance to the piece on the left from the little charge q? Obviously a plus something. Yeah, L over 4. I guess for now we'll kind of like that. L over 4 quantity squared. And then the second piece? Yeah. Oops. Make that legible. Any question about what happened so far? You see what the terms represent. So this is a lot like our triangle. This guy is feeling a force from two other charges, both from this one and from that one. They both follow Coulomb's law. The only difference is this distance is different, so it's not just a doubling of the same expression. This distance is a plus quarter L, a plus 3/4 L, right? What would F3 look like if I wanted to approximate for three pieces? So the picture now is, here's Q, here's this guy broken into three pieces, Q over 3, Q over 3, Q over 3. This is still A, and no, L, this is A. F3, it's going to have, magnitude, three terms, K, Q over 3. Three terms, obviously. I can obviously factor out my, I missed my little q. Just put it here. So what are these distances? First one is okay, so what if I wanted to start thinking about, obviously you can see that this is kind of tending towards something related to a series solution. What if I wanted to start thinking about writing this expression in terms of n so that I can make a generalizable expression such that maybe I could plug it into a spreadsheet. I've already done that for you. So you can see what the effect is of having higher numbers of n. But I need an expression that's obviously in terms of n, not in terms of 1, 2, or 3 in particular. And obviously right here I'm like, you know what, I can probably replace this with something. That's going to be a q over n. Q over n. Q over n. So what's the distance for these pieces going to look like? It's always going to be a plus. And how would you write those in terms of n? Yes, say it again.
L is divided by 2n.
L is divided, yeah, right. So if you look at this piece, this size is L over n, right? And each time when you get to the front, and that would be true here. This is also L over n because it's L over 2. This is L over 3. And as we go up, it's going to always follow that pattern. But we don't want that whole. We want half of that. So this first term is that. And there's nothing else because that is the whole distance for the first charge. But then this guy is farther by this amount. What is that amount? Yeah, so the same first push it to here is the exact same expression that we had. So there's a 2n, but there's another term in the denominator, right? And this is, right, L over n. Because that distance is this distance, which is also this distance, which means what? I mean, what happens this last term?
You add another L over n?
You do. And so this is, first you have to have that, because that gets us to here. The 1 L over n for here gets us to the second charge. You add another L over n, plus there's another L over n to get to, plus another there's going to be these two L over N's. Well, there ought to be a way to, somehow write a series version of this guy, right? So how are you going to make that look pretty? Because what we're going to want to do is something like this. The force on 3 equals some kind of a sum equals, lower limit, upper limit. And of course, it's going to have a k times little q. I'm going to write first big Q over n. And how are we going to make this thing work out so it looks right? A plus L over 2n is a given. But then how am I going to write this so that there's a term that relates to I? Why don't you stare at that for a minute, and maybe literally a minute, and see if you can come up with an expression that works. So that if I did I equals something to 3, that it's going to give me this. Say it again.
I L over n.
What's your, there are different ways to do it. Depends on what your I values go from.
Starts at 0.
If you do 0 to n, let's see what happens. 0 to, let's say n equals 3 in this case. So the 0th term gives me nothing here, and you just get that, right? You put in the second term, and you're going to get, so I equals, no, wait a minute, because you had to have a 0 and a 1, right? So you run into troubles there, right? Because if you had, let's say you go back to the 1 case, it obviously needs to work for that. So in that case, you'd have this guy equaling, you'd have I starting at 0, and you'd also have to, 1 piece was where we started. So you'd have 2 terms, which we can't have.
Yeah.
So what are you going to do then?
Either just start I at 1 and subtract 1.
Yeah, or what's the easy thing on the, the limit here? You could just adjust it to make it n minus 1, right?
Yeah.
So how about if we do that, from I equals 0 to n minus 1, then that works out fantastically. And yeah, you can obviously either leave that in n or fix it here or vice versa, but easiest thing is probably just to do that. And then we have an equation that we can test. And that means, how do I mean test it? Well, it would be interesting if we could plug numbers in and see how much it matters. Yes?
Are the denominators all supposed to be squared?
Oh, yes, they are. Thank you for pointing that out. Yes, they absolutely are. And I did remember to do that when I made the spreadsheet. So, yes?
Now the n in the series, the n minus 1,
Yep.
is that different from the n in the denominator then? Is that just like the
N- s-
number n?
So the n is going to remain what we've been talking about, like how many pieces have you chopped it in, but the iteration part, the I, like do you actually iterate such that you get, not just 1 term, but 2 terms or 3 terms or 4 terms. Every time you chop it into another piece, it adds on 1 more term to the sum, and that's why we need the I to iterate through. And how much you're adding, well, it depends on, the first, in this case of 3 pieces, you get 1 times L over n. Well, 0 L over n's, if you think about it like this, if you think about in the first term it's a 0, in the second term it's a 1, in the third term it's really a 2, right? And if we had 5 terms, it would be first term is a 0, 1, a 2, a 3, and a 4, right? Okay, so I have that in a spreadsheet. And where are you? What I did, I got rid of this guy, all of this stuff. I just made 1, so that we can really compare the effect of changing n. And what you end up finding is that that's the wrong one. Where's the other one? Here it is. No, that's my course. Well, if you want to know what my schedule is, where did you go? You know what? We're also out of time. Why don't we, we'll talk about how that series converges and then how to turn it into calculus and make it an integral next time, all right? All right, have a good one. Thanks for coming, by the way. And see you Wednesday.